Hello everyone, welcome back to the CM part of our course. And today we will discuss the local estimation procedure in the CM. This is relatively new procedure and this is cutting edge procedure which is still in development. But important to say that this procedure allows us to do much more what was limited in the global estimation procedure. So today we will discuss the difference between global and local estimations and the piecewise CM. Also, we will learn the model fit and model comparison in this local estimation and how to use the categorical data in the piecewise CM. So let's start with global versus local estimations. In our previous lectures, we learned the global estimation procedure. And this procedure studies the relationship among the network of variables by reproducing a single covariance matrix. And we refer to it as the global estimation because this variance covariance matrix captures all relationship among our variables at once. But as you remember, this approach comes with a number of assumptions about our data, such as a multivariate normal and sufficiently replicated data, and we need this to generate the unbiased estimates for our parameters. However, as we all know, most of our data, and particularly in ecology and biology, they violate these assumptions. And given the difficulty with which these data are collected and the complexity of interactions and the effects in our study systems that we need to assess, we usually we have issue usually with the power needed to estimate such a complex systems. And as you remember, this is the protocol, what we do if we have the violated assumptions of the covariance-based CM. So what we can do in LA1 to account for these assumptions. So the variance covariance-based method have been extended to consider the special cases such as not normal data or missing data and others. But we have the alternative estimation procedure, which is the piecewise CM. And this model was proposed not so long time ago in 2002 by Bill Shipley in the paper that you can see here. And this estimation procedure is based on the graph theory concept. And in this method, the relationship for each of our response variable in the CM, which are endogenous variables like y1, y2, they are estimated separately in the submodels for each response variables, and then they are stringed together in order to create the CEM. So that's why we call it local estimation or piecewise CEM, because of the nature by which the submodel are pieced together like a puzzles here in order to build the entire CEM network. And now let's consider a model example to see the differences between the global and local estimation procedure. For this, we will assume the linear relationship in our model. So what global estimation procedure does, it takes the set of all of this relationship in our model and reproduce a single covariance matrix for this all relationship as a one piece. And local estimation procedure also consider all relationship in the model, but for each response variable, it fit the submodel separately as shown here. And then it strings the inferences together, and only in this way it assesses the fit for the entire model. So it doesn't consider all relationship as a one piece, but rather as a submodels. And the great thing is that we have the package in R called piecewise CEM, which adapts this local estimation procedure. It was created not so long time ago by John Levchik. You can see paper here. And this package specifically is made for the natural sciences, for ecology, evolution, and other natural sciences. And as you can see here, the CRAN information, the package, the new version of package is developed in collaboration of John Levchik, Jared Burns, and James Grace. And these are all three leaders in adapting the CM to needs of ecology, evolution, and other natural sciences. And here in this link, you can see the vignettes for the piecewise CM, which has a lot of good information which you can read through. Another great resource is a book by John Levchik on his GitHub page, which is open online. And this book has procedures not only for local estimation, but also for global estimation. And I use quite a lot of material from this book for our course. And I want also to acknowledge John because he always responds very quickly to the questions. I asked him quite a few questions which were not covered by the book, and he very quickly responds and explains things. And now let's take our example in the piecewise CM in R. For our course, we will use the development version of the piecewise CM package, which you can install using the script here. Don't forget to load the library of the piecewise CM package after that. So the first thing what is done, we have to break down our CM model into submodels for each our response variable as shown here. And then each of these submodel is fitted separately as I show here in the script. But the piecewise approach does not release us from all assumptions associated with the statistical tests. So if we assume linear relationship, the data must still meet the assumptions of the individual models. For example, most linear regression assume constant variance and independence of errors. So we plot our models and we see whether our assumptions are not violated. So, and when we agree with the assumptions, we can then bind the inferences of these models using the piecewise CM package. The main function as the main workhouse function in the piecewise CM is the function PCEM. So it binds together our inferences of our submodels. You can list the submodels within this function, or you can just use M1, M2, which are defined above. So both ways are okay. Here you see the syntax which can be used for the models. So you know that the single tilde is regression, double tilde is correlation, and you can see here the percent and double tilde signs. It can be used to show the correlated errors in the model. And before we are getting to the model fit, we can examine our fitted model. For this, we simply call the model which we fitted above. And this will return the output which show each our submodel, their classes which are LM here, and the snippet of our data. Also, we can plot our model using function plot. It's not perfect, it's still very limited, but I think it works when we want to see how data look like or if we have a simple model. Here I summarize the differences between the covariance-based CM and the piecewise CM, or global and local estimation. So you can see that if we have the violations of assumptions of normal distribution of residuals and non-constant error distribution, then generalized linear models can be fit for data that are not Gaussian, such as count, proportion, binary data. Also, if data samples are not independent, then mixed effects or hierarchical models can be fit to the data, which are nested or have some predefined structure. Similarly, non-independent, such as spatial, temporal data, can be incorporated into the model structure to provide more robust parameter estimates. Also, the sample size is a problem in a global estimation. So here, only enough data is needed to be able to fit and to estimate each individual regression model. So in doing so, this method relaxes many of the assumptions associated with the global estimation procedure. And it better reflects the types and the quantity of data collected by our field, by natural sciences, especially in ecology. Of course, as I mentioned, that by doing this, the piecewise approach does not release us of the assumptions associated with the single submodel, such as if I assume linear relationships, then we have to see if the constant variance and independence of errors are not violated. And these assumptions can be easily checked by histograms or residual plots or QQ plots. Also, as you remember, the goodness of fit for the global estimation is based on the comparison of the modeled covariance matrix to the observed covariance matrix. And that's why we have one simultaneous solution, one single solution for the model fit. It is not the same in the piecewise CM because we have the covariance matrices estimated separately for each submodel, and then we have the multiple solutions for model fit because these solutions are modularized based on each separate submodel. And these multiple solutions in the piecewise CM are binded together by a specific method created by Shipley. And he created this method based on the path diagram on the method so-called directed acyclic graphs. But it is important to point out here that in the local estimation, we can use only the recursive models, so those that have no bidirectional relationships. And here I would like to recall what we know about non-recursive or cyclic versus recursive or acyclic models. So non-recursive models have bidirectional links or feedbacks. So here on this example, y1 affects y2 and at the same time y2 affects y1. And recursive models are those that have only causal effects which are unidirectional. So we know the specific direction of the effect between two variables here. And as I mentioned before, that only recursive or acyclic models are allowed in the piecewise CEM. So local estimation is unsuitable for approaches that need non-recursive models. For this, one needs to resort to a global approach. So first, let's recall what is the concept of the goodness of fit. The question that goodness of fit asks whether the model fits the data also means whether the model represents the data well, but this in CM means whether we're missing any important information. And the missing links means missing processes in a study system. And if we are missing important links in our model, the parameter estimates may be not correct and our model might be unspecified. So let's talk how to assess model fit in the piecewise CM. When we tested the missing links in the global estimation procedure in Lavaan, we used the modification indices that helped us to test which links can be included in the model. A similar procedure we have in the piecewise CM, which called directed separation test. So two variables are said to be directly separated if they are statistically independent, conditional on their joint influences. So x1 and y2 are directly separated. They are independent, but this independence is conditional on y1 because x1 affects y2 indirectly through y1. So let's unpack this statement. Independent means separated directly or causally not related. So there are no directed paths connecting these two variables, like between x1 and y2. And the test of directed separation asks whether the two variables are significantly not related or that their relationship in fact not different from zero. And the statement conditional on their joint influences, this is shown in red here, means that the test of statistical independence account for contributions from other variables which are connected to our variables that we test. So in other words, the test considers the partial effect of x1 on y2 if they are related to other variables or if they are related through other variable in the model. And this missing link, which we want to test in our model, is called independence claim. And this is the independence claim which we want to test in our model. So we say that x1 is and y2 are independent and conditioned on y1. So you may see this claim written in the following notation, where the bar here, it states the independence claim and the condition and variable here follow in parentheses. And with this, we say that we test the partial effect of x1 on y2 given y1 here. And model can have many independence claims, many missing links. In our case, it's only one link here indeed. And the set of independence claims that we want to test is called basis set. And basis set is the minimum number of independence claims derived from our path diagram. And what does it mean minimum? It means that the effect of x1 on y2 is only in one direction. So we do not test both directions of effects, but only one of them. Technically, the procedure behind the test of directed separation is that it fit submodel including missing link. For instance, we would fit the submodel for y2, which includes not only y1, but also x1 as a predictor here. And then it checks the significance of the b1 coefficient for our missing link. So if this missing link is significant, then we would reject our hypothesized model, and the directed separation test would suggest including the missing link into our model. Now let's look how it's done in the piecewise SEM in R. So the first step is to know what is our basis set of independence claims. This can be checked using function basis set of our fitted piecewise SEM model. And here is the output, and it says that there is a single independence claim representing the missing path from x1 and y2, which is conditional on y1 here. And the test of directed separation in piecewise SEM is performed using function dsep to our fitted piecewise SEM model. And here is the result, and it shows the result for the model fitted with the missing link. So this is our model here with the missing link, which includes x1 in addition to y1 for our submodel y2. And it shows that this effect is not statistically significant. It says that missing effect is not different from zero. We can get the same results if we feed this model manually. For instance, it's shown here, and the summary functions show exactly the same p-value for us. So this means that our hypothesized model is true, and we don't need any modification because our hypothesized model already includes all important links in our model. And now the most important contribution of Bill Shipley was that he showed that these p-values for each submodel can be summed together, and in this way we get the model fit for our entire SEM model. So here you can see the formula where p is the p-value from the d-separation test for each independence claims that we have. So here we have only one, but in the models we can have many of them. And K is the number of independence claims in the basis set, and Y is our is claim in a model. So the sum of these p-values for each tested missing link in a model would be our model fit for the SEM model, which is called Fisher-C statistic. Very important thing also that Shipley showed that this Fisher-C is chi-square distributed with 2k degrees of freedom, and k is the number of independence claims. So this means that we can use our C value and calculate the model-wide p-value from the chi-square table. And the same as we have in the Lavan, in our global estimation, we look for the p-value larger than 0.05. Because it implies that the hypothesized model is supported by our data. So in other words, there are no potentially significant missing paths were excluded from our model. And then Fisher-C statistic is used to calculate the AIC, archaic information criteria for our SEM model, where K here is the likelihood degrees of freedom. And then also the AIC lowercase c, which is the AIC corrected for the sample size, is calculated by adding penalty for the sample size. It is important to point out also here that like in the global estimation procedure for chi-square statistic, The Fisher statistic is also dependent on the sample size. So as a sample size increases, the probability of getting significant p-value increases. So this reducing the potential for a good fitting model. And here I would like to show you how this is done in R. For calculating Fisher-C statistic for our model, we can use function Fisher-C to our fitted model. And this will give us output. So this is our model fit. We have the C value, the degrees of freedom, and the P value. And the degrees of freedom, as you remember, is 2 multiplied per K. And K is a number of independent claims. So we have one independence claim multiplied per 2, and we have 2 degrees of freedom. So this is Fisher-C statistic, which formula is shown here, and which we can calculate manually as well using this formula. So we have only one independence claim, so we don't have a sum here, but we extract p-value for the submodel, which includes the missing link, which is shown here, and then we take log of that and multiply it per -2, the same what is done with the formula. And the result is exactly matching the automatic results done by the Fisher-C statistic for our model. Also, with our degrees of freedom, we find the p-values for our Fisher-C statistic, which is exactly matching also our results. As you remember, the AIC is calculated by C plus 2K, and this can be extracted using simply the AIC function to our fitted model. And if you want also to calculate the AIC corrected for the sample size, you use AIC C equals true here. And because we want to get the AIC specifically for the Fisher-C statistic, we have to mention here AIC dot type equal D sep from this separation test. And I will explain you why we have to do it, because we have another fit measures which we will consider next. Very recently, only a few years ago, Shipley proposed additional measure of model fit, which is called chi-square statistic. Is similar to our global estimation SEM. And this procedure is based on log likelihood approach, and it compares our fitted submodel to the fully saturated submodel. So it takes our model with the missing link for response variable and fit it to the submodel, which would include all possible links in this model. And then it compares it using the log likelihood test or chi-square difference test, which we have tried in our previous lectures. And if the chi-square difference test says that the more complex model is more statistically adequate, then we would reject our hypothetical model and would modify it by including the missing links. But in case if our chi-square difference test says that these two models are not statistically different, then we would choose our fitted model as more parsimonious one. And then this procedure is extended to the entire CM, where it first incorporates all missing passes from the model, and then it takes the difference in this log likelihood for each submodel between the proposed model and one that have all passes that are missing. And then it summarizes these differences to get an overall index of model fit. And here is the formula to calculate the chi-square for our CM model, the fit for our CM model. And here in this formula, we see that we take the difference between the log likelihood of our fitted submodel and log likelihood of the fully saturated submodel. So we have a submodel without a link and the submodel which includes all missing links. And then we take the sum across all submodels in our CM model. And also the AIC can be calculated as the sum across AICs of each our fitted submodels. The same can be calculated for the AIC corrected for the sample size. And in the piecewise CM, we can get the chi-square using the function LL chi-square to our fitted model, which gives us the chi-square value, the degrees of freedom, and the associated p-value. And if we recall our formula, of course, we can calculate this manually as well. And as you remember, we calculate log likelihood ratio for each submodel, and then we take the sum of it multiplied per -2. And log likelihood ratio is our fitted model with missing link minus log likelihood of the saturated model, which includes the missing links. So we have this for our first submodel, for our Y2 as a response, and for our second submodel, for our Y1 as a response. For the second submodel, of course, we don't have missing links, so it simply would be equal to 0. And the result gives us exactly the same chi-square as a LL chi-square function here. And with 1 degrees of freedom, we get our p-value, which is also exactly the same as our function. And AIC, which is the sum of AICs for all our submodels, is obtained by the function AIC to our fitted model. And also, if we say that AIC C equal true, we get the AIC corrected for the sample size. And the AIC for the chi-square statistic is a default in the piecewise CM. So if we want to get AIC based on the Fisher-C statistic, we have to specify this as a D-separation test, as the same as I showed in the previous slides. And now you may wonder that if we have linear relationship in a model and if our data are multivariate normal as we have in our model, because we know this from our previous lectures on global estimation, then what would be the difference with the chi-square output from Lavaan? So let's test it. So here is a script of our model in Lavaan. As you remember, we use CM function, and here I do not call summary in order to save the space here, but I call the Lavaan inspect function and call only the fit values for chi-square and p-value. And here you see the output from Lavaan, which is exactly the same as we have from our piecewise CM. So we can say that the model that assume multivariate normality, as we do here, the chi-square statistic and p-value, they are actually the same, which we obtained from Lavaan. And this exercise was a long work around to reveal that all of these functions we could get at once in the piecewise CM using the function summary to our piecewise CM fitted object. And the output gives us each submodel. It reports us the AAC for our model, and this AAC is the AAC for the chi-square as a default in here. And also it reports the D-separation test, so it tests the missing links. Also, we get here the goodness of fit of our entire CM model. We have both chi-square and Fisher-C statistics with p-values and degrees of freedom. Below here, you see the coefficients for our path for each of our link in the model, and the standardized coefficients are given by default, which is different as the Lavaan does. Also, R squared for each variable is also given by default in the piecewise CM. And if we would compare this summary output to the summary output of Lavaan, again, because we are making the same assumptions that our data are multivariate normal and the linear relationship, all of this output will be identical or nearly identical. So only if we incorporate different distributions of data or more complex model structures using mixed effect models, then we can get the different results. And now let's talk very briefly about model comparison in the piecewise CM. As an example, we will compare our model to model 2, which is here fully saturated. So I specify the second model in the piecewise CM, and then for chi-square difference test, we use a function ANOVA simply to compare our two models, and we know that model 1 is nested in model 2, so we allowed to do the chi-square difference test. So take care to arrange the correct order manually here, so that we have first our more complex model and second our simpler model, because in piecewise CM ANOVA function doesn't arrange it automatically. And the results here give us the information which we already know, that these models do not differ significantly. That's why we choose the simpler model, which is more parsimonious here. Also, we can use the AIC comparison. So we use function AIC for both our models, which will reproduce AIC for each model. And then we just calculate manually the delta AIC. And next, we will learn about the categorical data in piecewise CEM. And here is the protocol, what we do if we have the categorical variables. But this is only for the piecewise CM, which is quite similar table what we had for our Lavaan. So if we have exogenous categorical variables for binary and ordinal variables, we can treat them as numeric. We can create the separate dummy variables, or we can use them as a categorical variables and use approach marginal means in the piecewise CM, which I will show later. The same we do for the ordinal variables, but if we have nominal variables, we don't have other approach, only use them as a categorical variables with the marginal means approach. And if we have the endogenous categorical variables, then we can treat them only as numeric variables or to treat them as a dummy variables. But if they are nominal variables, unfortunately, there are no implementation in the piecewise CM. So now let's talk about what are the marginal means approach used in piecewise CM. So the marginal means are the expected average value of one predictor given the other covariables in the model. So as you know, all models can be used for prediction, and in multiple regression, the predicted value of one variable is computed while we hold the other variables at their mean. So marginal means are the averages of these predictions. And for categorical variables, these marginal means are particularly useful because they provide estimated mean for each level of each factor. So let's consider here a simple example. And for this, you can use data, CM data2 CSV file, which we have on the Blackboard. And here we have one response which is affected by the group. And this group has two levels, A and B. And the output or the summary output here gives the simple coefficient here, which is the effect of group B on Y in the absence of group A. And as we established in our previous lecture on categorical variables in Lavaan, as you remember, the intercept is simply the average of Y in a group A. And because this is a simple linear regression, the marginal means here for Y in group A and B are simply the means of the two subsets of the data, because they are not controlling for any other variables. So this predict here is simply the mean of Y in our group A, and the same we will have for the B if we calculate it. And now let's see what happens if we add the continuous covariate to our model, which is X here. So here, when we calculate the marginal means, these are evaluated while holding the covariate of X at its mean. So it controls for the effect of X on Y. And of course, then we can calculate the same for our group B. But this procedure will get even more complicated if we add a number of factor levels or the number of covariates. And there is a im-means package in R which allows easily to calculate this marginal means. So you can see here we have the marginal means calculated for our model for each group A and B, and they are exactly the same which we calculated by hand here. Also, this package im-means provides additional functionality by conducting the post hoc test of differences among the means of these two levels of factors. So for this, you have to use this script, which I show here, and this basically gives us the contrast between the means of groups A and B. And this is simply the Tukey test, which is comparing the difference between our levels of our factors. And this piecewise CM adapts this procedure that I have shown by im-means package. So for this, we use the function coefs coefficients to our piecewise CM fitted object. So it adapts this procedure by two steps. First, it computes the significance of the categorical variable using ANOVA, and then it reports the marginal means and the post hoc tests. And this will give the normal output for our continuous variable x, and also the standardized coefficients for that. And the significance test from the ANOVA is reported in a row corresponding to the group effect. And below also we have the marginal means here, estimates for our levels of the grouping factor. But also, you will notice here there are no standardized coefficients for the effect of group and also for the marginal means here. And this is because these are not linear coefficients and therefore they cannot be standardized as a usual way here. So what we can tell in general about this marginal means approach in piecewise CM that it provides a measure of whether the path between the exogenous categorical variable and the response are significant, as well as parameter for each level in the form of the model estimated marginal means. But we cannot get the standardized coefficients for that. And here on the slide, I again recall the protocol, what we do if we have the categorical variables in the piecewise CM. So again, if we have binary or ordinal variables, which are exogenous, we can treat them as numeric or create separate dummy variables or use them as categorical variables using marginal means approach. But nominal variables cannot be used in any other way except use them as a categorical with marginal means approach. And for endogenous variables, as I mentioned earlier, we adapt the steps 1 to 3 for binary and ordinal variables. But if they are nominal endogenous categorical variables, we cannot implement them in the piecewise CM. But this is yet, maybe in future we will have. And now your task will be to try this procedure yourself in the piecewise CM. For this, we use data from the project that you already know, but these are different data. So take care that you take the new data set from the Blackboard, which are called food web data 2 CSV file. And in this data, we have the grazing type, which is grazing by sheep, grazing by cattle, or mixed grazing. So these are nominal categorical data here. And also we have the food web length, which is numeric here, 1, 2, 3. So food web length increase, it's simply numeric. And then here is your hypothetical model. So you know the model from the previous lectures, but now food web length is a numeric here, and grazing it's a nominal categorical variable. So now your task is to take this grazing type variable, which is exogenous nominal categorical variable, and to test it as a part of this all CEM model on figure 1 using marginal means approach in piecewise CEM. So good luck to you with this task and looking forward to see you on the next lecture.